All right, guys, here we go. So, guys, you've already summarized chapter 19, and I suspect as a result, you probably had one of two experiences as you were reading through chapter 19. Some of you got done summarizing chapter 19, and you were thinking to yourself, "You've got to be kidding me." Some of you got done summarizing chapter 19 and you were thinking, hey, this could be kind of interesting. So guys, what we need to do is we need to find the middle ground between this. If you got into chapter 19 and you were thinking to yourself, you've got to be kidding. Frankly, that was my response too. Even with the degree in chemistry, it was, you've got to be kidding. Because just when you think you've got your arms wrapped around entropy and importantly, Gibbs free energy, which we're not going to talk about today, guys, all of a sudden this just blows up. So if you're the one that was going, you got to be kidding, understand, guys, our goal in this unit, in this chapter, is going to be to get you to understand what you need to know and nothing more. Okay. Now, for those of you that were looking at this and going, man, this is going to be good. It is. It's fascinating stuff. But guess what your goal is? To learn what you need to know and nothing more. Okay, guys, so we're going to stay in the middle. For those of you that are panicked, you're going to be okay. For those of you that are excited, you might feel a little squelched because, guys, this is crazy stuff. And as we dig into it, what we don't want to do is run down so many rabbit trails that we end up spinning in circles and everybody's spinning in circles, because that doesn't do anybody any good. So guys, we're going to talk about some of the crazy, but we're not going to major in crazy. You know what I'm saying? Okay, so guys, with that said, I think you're going to find this beneficial, but I want to turn it to you as a question. And guys, the question is this. You may want to write this down. Guys, what is the most important concept in chapter 19? And guys, as you're maybe pondering that, by the way, there is a right answer regardless of what your opinion is, but I do want to hear your opinions. Guys, at least you should understand that chapter 19 should be chapter 6, right? It should follow. The reason that it doesn't in our book is because Eugene felt like it was actually more important to understand equilibrium well first. And so they actually shoehorned chapter 17 in there to give you some equilibrium before we get into entropy. But guys, you understand enough about entropy that we can appropriately knock 5 and 19 up against each other and create one unit. So, guys, with that said, what do you think? And I know I'm sort of setting you up here going, there is a right answer, but there is. But guys, what would you say was the most important stuff in 19?
Kind of based on what you said.
Energy. Well, sort of. There's more. Heat is not the only form of energy, not the only transfer of energy we're going to talk about. There's another, let's say it this way. There's another way for processes to lose energy that doesn't cause a change in temperature. But then you guys came to this idea of work. Somebody said, I go, hey guys, there's another way to lose energy. And you're like, duh, it's work. And guys, we're not coming back to work. So it turns out there's another way for processes to lose energy other than heat, but it's also not work. And you'll see. And that's where we're headed. It's disorder. And guys, what you're going to find out is that never, it sounds weird, guys, in this class, never think of order. If you find your brain looking at something and going, hey, that is more ordered than this, stop yourself immediately. The way that you've got to think about it is this is more disordered than that. So guys, that's not trivial. Why does it matter that you think about disorder rather than order? What does that change? The signs. Guys, if something becomes more disordered, that is a positive change in disorder. If something becomes more ordered, if you're thinking about order and if something's getting organized, and if you think, so you've got your room and it's all messed up, and then your mom goes, go clean your room, and now your room is clean, now you're thinking order went up. And we're not going to think about it that way. We're going to think of it as disorder went down. Go ahead. Yeah, because you had to do work. Well, let's talk about clean your room, because cleaning your room requires you doing work, right? So literally what you're doing is you're adding energy you're increasing the energy of your room by doing work, and that literally force and distance. And as you're cleaning your room, you're causing the disorder to go down because you're doing work. Yeah. Go ahead, Doug. It depends on how big a mess your room is. In theory, it could be, because your room can then spontaneously go back to a mess. Some of you are like, hey, it's not my fault, it's science. But we're going to get there in a couple days. The idea is that all processes in our universe tend towards conditions of greater disorder. Second law of thermodynamics. We'll talk more later. So the natural state of your room is disorder. And so to work against that, you have to add energy. And as you add energy, as you create decreased disorder, that then provides the potential for your room to get messed up again, which would be a net release of energy. So yeah, actually, like bringing that full circle, yeah, nature can store energy in the form of lower disorder. So an example would be this. And guys, this isn't just trivial. This is interesting and important. Crystals. Guys, crystals have very, very low disorders. If you look at a salt, and we're going to watch a video of this in a minute. If you look at a salt, you can clearly see, and I'm going to say this wrong, but hear me out. You can clearly see that this is very ordered. And there actually is energy stored in that. And so the idea is that this has a low disorder, and there's a component of energy that's stored in low disorder. But guys, you still haven't hit on the most important concept in chapter 19. These are all means to the end, but they are not the end in themselves. Okay, so and that's where this comes together. So guys, let's but you're not quite there. But guys, this is the map. What did we talk about in chapter 5? What was the big idea? Enthalpy. At the beginning of chapter 19, we're going to talk about everything we just talked about with entropy. And when we bring those together, that brings us to what's called free energy or Gibbs free energy. So you're going to find the sum, the sum of enthalpy and entropy is Gibbs free energy. But we're still not there. What is the most important concept in chapter 19? What's that? Not energy. Guys, this is where this is headed. This is what you're going to see on the AP test. Do I really have to just tell you? Guys, the answer is spontaneity. So, guys, and we're going to start by talking about this. But you want to write it down. Guys, the most important thing that you're going to learn, and this is how we're going to wrap up this unit next week. Guys, the most important thing that you're going to learn, I don't know a better way to, is spontaneity. But let me say that differently. Why is this the most important thing in the unit? Because this is what the AP testers are going to test you over. Guys, chapter 5 and chapter 19 has all been leading up to spontaneity. We'll define it in a minute, but let me just sort of give it to you loosely right now. Guys, spontaneous processes are things that happen on their own. You don't have to force them to go. They go on their own. So guys, this is the big idea. And specifically, this is where you'll know the unit is over when you can answer this question. Under what conditions is any particular reaction spontaneous? When you can answer that question, you know that you're done with this unit. Do you see how that goes? And guys, the answer to that is what you were talking about. It's all about Gibbs free energy. So we're building to Gibbs free energy, which then answers the question, what things are spontaneous? So do you get the big idea? Okay, so guys, with that said, let's sort of back out of this a little bit and let's talk. So guys, the most important thing then in this unit are spontaneous processes or reactions. So let's define it. Our definition is going to be this. A spontaneous process is, for chemistry, a reaction that takes place without any outside intervention. So guys, what I'd like to do is I'd like to give you some examples. But before we do, we need to answer the question, what is it that makes a process spontaneous? And guys, the answer is this. So what characteristics make a reaction spontaneous? And guys, the answer is this. They lose energy. Why do atoms bond together to make molecules? They lose energy. What do you have to do to get them to break apart? Add the energy back. Guys, the idea is that things happen in our universe because they are energy losers. That might be worth underlining. Things that are spontaneous in our universe, guys, are things that lose energy. So guys, let me give you some examples. I don't know if you need to write them down, but just make sure this is jiving with your thinking. So an example of this would be a ball rolling downhill. Or if you prefer, you can think about the metal block that we played with the first day of this unit falling. So guys, do balls roll downhill? Every time. So if you've got a hill, and if you've got a ball, and if the ball's here, it's going to roll downhill. But guys, what if the ball's at the bottom? Does it ever roll uphill? No. Could it go uphill? Yeah, you got to do some work. We'll talk more about that later. But guys, balls always roll downhill. They never roll uphill. So let's talk about where the loss of energy is going on. What kind of energy are we losing? Potential energy, because the ball has more potential energy at the top than the bottom, and as that potential energy is lost, the ball rolls downhill. So we can clearly see our loss of energy. Is that okay? Okay, so guys, I'm actually going to switch the next two. I'm going to change your notes up a little bit because I think this conversation will go, I think this one could have been confusing if I did it next. So guys, we understand that balls spontaneously roll downhill. Let me give you another example. Nails rusting. So guys, you take a nail and you set it out in your lawn. That's stupid, but you take a nail and you set it outside. Do you have to do anything to get that thing to rust? No, it's going to rust, right? Why does that happen? Well, it's losing energy. Guys, do you remember from last year? How does it lose energy? In what form? Well, that's the reaction. It's an oxidation reaction. But how does it lose energy? In what form? It's actually heat. Yeah, it's actually heat, guys. That when a nail rusts, it loses energy in the form of heat. It just happens so slowly that it doesn't get hot. But guys, maybe you I don't have one here. Maybe you understand this. Those hot packs that you can buy at like Walmart for $1, and you open up the bag and you shake them, and it looks like sort of like a tea bag, and you hang onto that thing and it feels warm. Jessica, you okay? I don't want you to miss this, so I'll wait for what you're doing. Go ahead. You're okay? So guys, the idea then is this, that same reaction that is causing a nail to rust is the same reaction that takes place inside of a hot pack. Did you guys know that? That it's actually just a bunch of ground up iron inside of there, and when you rip the bag open, it exposes the iron to the air, and the iron rusts, and it actually releases heat. So why does it go faster for the hot pack than the nail? Surface area. Yeah, it's all about surface area. So guys, you good on that? So what about the, and by the way, when you rip open the hot pack, do you have to do anything to get it to go? No, it just goes. So here's another example. Hydrocarbons burning. Guys, the question becomes this. Do you have to do anything to get a hydrocarbon to burn? Thank goodness, yes. Right? Because if you didn't, you open up the Bunsen burner tap and it bursts into flames. So now we need to talk. Is this still spontaneous? And guys, the answer is yes. So think about it this way. Sometimes you will need an initial addition of energy. Activation energy, we'll talk more later. But guys, sometimes you do need an initial addition of energy to get it started. But once you've, like the spark, or once you've added that little bit of energy, if you don't have to keep sparking it, we know that's a spontaneous process. So guys, don't get confused about that. An initial addition of energy does not mean that it isn't spontaneous. It just means you got to get it started. So are we good on this idea? Go ahead.
So I just have a question about like the sparkling stuff. So
Yeah.
if you were to have a room
Okay.
filled with, I don't know, like half regular air and half like that's a hydrocarbon.
Yeah.
And you slowly heated the room,
Uh-huh.
would it suddenly just like all explode?
Yeah, absolutely. Because, well, assuming that they were mixed,
Yeah.
right? So, but yeah, absolutely. Eventually you come to what's called the flash point. Is that point where it ignites, right? Ray Bradbury, Fahrenheit 451. You got to heat paper up to 451 degrees before it ignites. So there's a temperature at which combustion begins. What happens at that temperature? No, but what happens in, so what happens inside a paper at 451 degrees that then causes it to burst into flames? The atoms start to break, the bonds break, right? And then the cellulose breaks down into elements. Now you've got free carbon and hydrogen from the cellulose that can react with the oxygen and make carbon dioxide and water. You guys good? Go ahead, Mark.
About the hydrocarbon burning is like when you push the ball up the hill.
Yeah.
You keep pushing it or else it will climb the hill.
Yeah.
And the hydrocarbon just like
Yeah, yeah, I agree. And so maybe what about this? What if we could put the ball right at the top of the hill? You got to give it a push to get it started, right? But then once it goes, it goes. Unlike pushing up the hill, you got to keep pushing. Are you guys clear on the idea? Does this sit okay? Because I'm about to throw you a big old curveball. You ready? Okay, so guys, if you're ready to move forward, you can all agree with the statement that says things that are spontaneous, which means happens without outside intervention, other than the initial nudge, if necessary. Things that are spontaneous lose energy to their surroundings. We have an example of kinetic energy decreasing. We have an example of heat being released, whether it be slow in the case of a rusting nail or faster with a hot pack. And then hydrocarbons burning, that is clearly exothermic, dumping energy. It heats our room and boils our water in lab. You guys good? All right. So guys, if you're comfortable with that, in order to understand the beginning of chapter 19, you've got to make sense of this crisis. Quick cold packs. So guys, here in my little first aid kit, I have a quick cold pack. And if you aren't familiar with these things, this is actually a bag with an inner bladder, and then you can clearly hear the pellets that surround that inner bladder. It's probably worth you understanding the chemistry. Guys, this is actually what's going on. Inside of this, oh no, sorry, no, stop, bad. Wrong ammonium compound. So guys, this is actually what's going on inside of a quick cold pack. You actually have what's called ammonium nitrate. Those are the pellets. And then inside this inner bladder, it's just simply a bag of water. And when you squish this, it breaks the bladder. And when you do, the ammonium nitrate goes into the water and it simply dissolves. But as it dissolves, is it endo or exothermic? Is energy going out or going in? Why? How do you know energy is going in? Because it feels cold. And guys, understand, cold is not a thing. Cold is the absence of heat. So what's going on is as this process takes place, it is sucking energy in from the environment or your injury, and it's sucking energy out of the surroundings and into the system. Now guys, do you have to do anything to get this reaction to take place? So when you break this bladder, do you have to continue to shake it to keep it cold? No. All you have to do is start the process, and then this happens on its own. So is it spontaneous? Yes. Guys, this is a spontaneous process, but it violates this rule because it doesn't seem to be losing energy. Do you get the idea? You okay? Because guys, here comes the problem. This thing is actually losing energy, just not in the form of heat. Is it doing work? No, it's not getting bigger. So guys, how is it losing energy if it is taking in heat and it's not doing work? Well, guys, you're going to find out the answer in just a minute. I need to know that you understand the crisis. Because, guys, we've got this idea that spontaneous things lose energy, and now we're finding out that some things are spontaneous, but they don't give off heat. They actually take in heat, which currently is a contradiction to what you understand. You guys okay? Okay. So, guys, before we can finally unpack this, you don't need to write this down, but let me just lay this at your feet, and then we're going to do some terminology, and then we're going to move forward. So guys, energy has got to be lost to the surroundings in order for a reaction to take place. So guys, the question that we have before us then is, how do we explain the way a quick cold pack works? Well guys, what you're going to find out is that our definition of energy is too narrow. But in order to expand our definition of energy, we need some terms. So guys, write these down with me, and then we're going to come back to the quick cold pack. So guys, the first thing that you need to understand is the term reversible process. So guys, a reversible process by definition, and you need to write this down word for word if you're taking notes. A reversible process is a process in which it is possible to return a system to its original state with no net change in either the system or the surroundings. This is what is called a reversible process. So it's a process in which it is possible to return a system to its original state with no net change in the system or the surroundings. Now guys, this is hard to picture. I like the example they give in the book. This is redundant, but it doesn't make sense for me to bring you another example because this one is so easy to visualize. I would encourage you to write this down with me. Guys, imagine a cup and this is a perfect insulator. Energy is not going into the room. Imagine a cup of ice water. Those are ice cubes. Guys, imagine a perfectly insulated cup of ice water at 0 degrees Celsius. Is that melting or freezing? Both. It is melting and freezing at the same time. So guys, now zoom in at a molecular level. So if you zoom into this mentally at a molecular level, what you see is this. Here's an ice cube, and here's liquid water. And guys, let's focus on one molecule of liquid water and on the crystal of ice. So here's the idea. Which has more energy, the liquid water or the ice? The liquid water, because it's got a little bit of freedom. It's moving around. Now the idea is this. When the liquid water bumps into the ice crystal, what does it do? Well, it releases energy. And where does that energy go? Into the crystal. And as this hits and releases energy, that energy is transferred to one of these frozen water molecules. This guy goes into solution and this guy goes stuck to the ice. And what's the net change? 0. Guys, that is what we're talking about when we say a reversible process. Liquid water and ice at 0 degrees Celsius, and this is the key, is both freezing and melting at the same time with no net change in either one. And guys, that's what it means to be reversible. But guys, here's the thing. You've already studied reversible processes before. What do we call things that are going forward and backward at the same time? Equilibrium. And guys, that is actually the definition of equilibrium. An equilibrium system is a system that is reversible. It goes forward and backward with no net change to the system or the surroundings. So when you think reversible, think equilibrium. So guys, let's get through the other two terms and then we'll do questions. Let's do the other two terms. Reversible. So guys, by definition, an irreversible process is a process which cannot be undone simply by reversing the events that caused it. Now guys, don't be confused. That does not mean that it can't go backwards. It can, but through a different pathway. And now guys, there's one more term and then we're going to bring these three ideas together. So it goes like this. Guys, the last term that we need to talk about then, oh, and we should mention this, that different pathway has different values for work and heat. You okay? Now guys, the last term that we need to talk about is spontaneous process. And you're going, wait a minute, we already talked about this. We did. But let's talk about it again. Guys, what does it mean if something is spontaneous? What did you learn earlier? What does that mean? Happens on its own without any outside intervention. Well, guys, it turns out that, and that's true, we're not going to change that, but guys, spontaneity is actually connected to reversibility. And it goes like this. Yes, a spontaneous process does proceed on its own without any outside intervention. We're not changing that. What we are doing is acknowledging that these things always have a direction in which they occur. And as a result, they're irreversible. And then we're going to talk about it. guys okay? Can we, just a second, Mark. I'm gonna lead for a second because I want to make sure we all get to the same point before we start asking questions. You guys okay? So guys, let's bring these three ideas together and let's talk first of all about balls rolling down a hill. Is a ball rolling down a hill reversible or irreversible? So let's talk about what that means. It means it's a process which cannot be undone simply by reversing the events. So guys, do balls always roll downhill? Yeah, do they ever roll uphill? No. Can we make it go uphill? Yeah, and that's what this is saying. It can go backwards. But guys, if it's going to go backwards, it goes through a different path. And when we say path, we don't mean it doesn't roll up a different hill. We mean that it's different amounts of work and heat. So guys, the ball rolls downhill all by itself. To make it go back up, we've got to do work on it to make it go up. Does that make sense? Okay, now what about this? If this is energy initial and if this is energy final, how do we find the amount of energy that's lost when it rolls down? Just subtract, right? But guys, what about this? What if we pushed it back up to the top? What would that energy change be? It'd be the same. So guys, understand the energy change is the same. The difference is how it happens. When the ball goes back up, we've got to do work that we didn't have to do coming down. That's what it means that they have different amounts of work and heat, because when the ball rolls downhill, it's just releasing energy, and actually a lot of times in the form of heat as it's creating friction and air resistance and all that other stuff, or when it gets to the bottom and hits something. But guys, to make it go back up, we've got to actually do work to push it back uphill. So the heat and work values are different, but the energy change is the same. So what about a nail rusting? So guys, when we talk about a rusty nail, is that, oh gosh. So guys, when we talk about a rusty nail, is that reversible or is that irreversible? Irreversible. You set the nail out and it rusts. Now guys, can we take that rusted nail and turn it back into iron and oxygen? Oh yeah, but it takes a lot of work. So guys, what that means is that the rusting of a nail is irreversible. Now guys, notice that we've called both of these things spontaneous, right? So now guys, what about burning hydrocarbons? When we burn hydrocarbons, can we take the carbon dioxide and then water and turn it back into methane and oxygen? Sure. But guys, that takes an amount of work. And so when we burn hydrocarbons, that is spontaneous. But again, it is irreversible as well. So guys, the bottom line is this. Anything that is spontaneous is irreversible. Doesn't mean it can't go backwards. It just means it doesn't go backwards with the same amount of work and heat being done as it did going forward. Does that make sense? Go ahead, Mark.
I'm just confused about reversible processes. I thought in the book, I read it that it said that
It said what?
I thought, I probably read it wrong, but I thought that it said that.
Oh no, anything at equilibrium is reversible. Yeah. Guys, other things you want to talk about? Yeah. Yes. So it's reversible and therefore at equilibrium. Boom. I was hoping somebody would say that. Guys, tease that out in your brain. Because Jeanette's going, wait a second. Can I bring it up? Jeanette's going, hang on a second. We got our thing of water, right? And so the idea is this. Is this stuff melting? Yeah. Is this stuff freezing? Yeah. At the same time, and Jeanette's going, wait a second, isn't it freezing and melting spontaneously? And the answer is yes. So guys, here's the way to wrap your brain around this. Be careful with this, but hear this out. Guys, reversible, hear this carefully, reversible processes, equilibrium, reversible processes are spontaneous in both directions. Let that soak in. Reversible processes are spontaneous in both directions. Irreversible processes have a direction they do go, they have a direction they don't go, and those are the things that we call spontaneous. So don't get muddled in this, but guys, if something is reversible, it's actually going both directions at once. But by definition, that does not mean spontaneous. Spontaneous means goes one way, can't go the other way, all on its own. So by that tight definition, that's what spontaneous means. Guys, if that doesn't make sense, think about it this way. If something is reversible, what do you see? Nothing. Does that make sense? It's going forward and back with no net change, so you see nothing. Guys, if something is spontaneous and therefore irreversible, what do you see? You see change. So guys, the idea then is that spontaneous, irreversible processes are doing stuff. Reversible processes, which are at equilibrium, they're doing stuff. You just don't know it because they're not going anywhere because they're undoing themselves. So maybe that helps. Go ahead. Is not spontaneous because it's reversible. And then, Luke, the idea is it is doing something. It's going in both directions. You just don't see anything happening. See how this kind of feels like a word game, but it's not? What other things do you want to talk about, y'all? We okay? Are we okay to go forward? So, guys, let's do this then. Let's tie all these ideas together by doing this. Quit out of this, move this over here. So, guys, let's take this and let's look at a different example. The egg drop. We animate it. Jessica, I saw your pictures. The hands you drew, super creepy. Yeah, just so you know. Okay, yeah, like I kind of felt bad for whoever that person was. All right, guys, here's the thing that's interesting. Let's have this conversation first. Dropping an egg, reversible or irreversible? Irreversible, right? It's not like you drop the egg and the egg goes splat and up and splat and up and splat and up. It goes splat and never goes up, right? Now, guys, here's the thing. You'll notice that this question doesn't say a thing about irreversibility. It talks about spontaneity. Why would they ask that if this thing is actually meant to represent reversibility? They're the same thing. Guys, if something is irreversible, by definition, it is spontaneous. So if this is irreversible, and you agreed that it is because it can't go in both directions, guys, that makes it spontaneous. So is this thing spontaneous? Well, yeah. You click on this and it falls and goes splat. So that's spontaneous. But guys, don't let the animation distract from the science. Because this has got what we call a spontaneous direction. Now, could we, in theory, take this mess, undo it, and lift the egg back up to the hand? Yeah. And guys, how much energy would that take? Exactly the same amount of energy that is lost when the egg fell and went splat. The difference is this. It would take a lot of work. So guys, the idea is if we were to reform this and lift it back up to the hand, it would require as much energy as lost when it went splat. The energy change is the same. The difference is how that energy changes. In order to make this go back to its original state would require work that wasn't done when it went splat. That's what makes it irreversible and therefore spontaneous. So will this ever go back up? Well, no, that never happens, so that is not spontaneous. And guys, this then is the way we talk about this. Dropping an egg is irreversible. Therefore, it has a spontaneous direction that it always goes, and it has a non-spontaneous direction that it never goes. Does that make sense? Go ahead, Susanna.
Are most chemical reactions spontaneous?
That's interesting. Are most chemical reactions spontaneous? And we'll say it this way. All of the chemical reactions that you've ever seen are spontaneous. Because if they weren't, they don't happen. Isn't that weird? But guys, that's actually the case. There are billions of chemical reactions out there that you've never seen because they're not spontaneous. And therefore they don't happen, and therefore we don't think of them as being chemical reactions. So every reaction that you've ever seen has to be spontaneous or it wouldn't be happening. Does that make sense? Go ahead, Luke.
So, like, are there reactions that have, like, resistance that are irreversible, but, like, they don't just happen on their own? So,
Help me understand what you mean by resistance.
So, like, an example would be, like, say, like, pushing a chair somewhere.
Mhm.
Like, if that was a reaction, then you don't just give it a nudge and it keeps on going. But at the same time, would that be, like, a reversible reaction?
No, that would be a reaction that doesn't take place. So that would be like pushing the ball uphill. That you can make it happen, but if you have to keep pushing, and if you stop pushing and it stops happening, then that would be an irreversible process that you're driving in the non-spontaneous direction. Is that okay? Jessica, hold on, Mark. Go ahead, Jessica. Yeah. But eventually it stops. Right. So don't go too far with the physics. Stick with the chemistry. If you have to push and keep pushing, then it's not spontaneous. Go ahead, Mark. Let's not. That's a whole no. You're right that would be non-spontaneous, but now we're in nuclear chem, and let's not go there. Okay. So, guys, let me take you here. So this then becomes the idea. You don't need to write any of this down. Just make sure you agree. So guys, when we look at this dropping egg, we know that there are two possible processes, up and down. We know that down is spontaneous and up is not. But this process then is irreversible. It's got a direction it does go, it's got a direction it doesn't go. Consequently, then it's spontaneous. And as Nathan said, you used the word like interchangeable. And they are. If you've got an irreversible reaction, it will be spontaneous. So guys, in this then, what is the net energy change for up and down? Well, it's zero. But guys, this then is interesting because we now know that energy change is not enough to determine spontaneity. So guys, the question then becomes this. What other factor must be going on in order to determine if a reaction is spontaneous? So to bring this together, let's go here. Take-home messages. Number one, spontaneous processes have a definite direction. Thought number two, spontaneous processes are irreversible. And thought number three, if a process is spontaneous, then the reverse process is never spontaneous. And then guys, finally, energy change is not enough to tell you whether or not it's spontaneous. And guys, if you're looking at that and going, take-home messages might be worth writing down, just go print the notes. I don't want to pause there long enough to let you get this down. So guys, let's do this then. Let's go back to our quick cold pack. So, reversible or irreversible? Irreversible. You smush the bladder, you mix them up, the reaction takes place, and you don't have to do anything, it goes on its own. So this is irreversible. It is also therefore spontaneous, but it also takes in energy. So guys, now we're ready to talk about it. Why is it that this reaction is spontaneous if it's taking in rather than giving off energy? And guys, it turns out that there is another driving force in this universe. And guys, this is where this gets weird, but you got to hear this. Typically, people are comfortable with the idea of heat going out. It makes sense that if you light a Bunsen burner, heat goes out and it just happens. It makes sense that balls roll downhill because you see them go and it just happens. Well, guys, it turns out that is not the only driving force in the universe that causes stuff to happen. Another one is randomness. And guys, I would encourage you to write this down with me. Draw this. Sorry, I'm sort of in the way. So guys, here's what we've got. We've got two gas cylinders. Imagine if you could two propane tanks stuck together with a hose. One of those propane tanks is full of propane. The other one's empty. It's a vacuum. There's nothing in there. That's what we're trying to represent here. So here's your empty propane tank. Here's your full propane tank. Now guys, when you open the valve and come back an hour later, what are you going to find? Both propane tanks are half full. And guys, understand, you don't have to do anything to get that to happen. When you come back an hour later, this is what you're going to find. So guys, now we need to connect this to an idea. We are going to call this process the spreading out of gases. So guys, the spreading out of gases, is it reversible or irreversible? Irreversible. So guys, this gas will travel in this direction. Would it ever be that we've got two half-full cylinders and all of a sudden this gas goes woohoo and goes back over there? No. So it's irreversible. So is it spontaneous? Yes. Guys, do we have to do anything to get this gas to spread out? Do we have to heat it? Do we have to squeeze it? No, it just does it. And guys, when this happens, the temperature doesn't change. So why does it happen? If the temperature doesn't change, and if we don't have to do work to get it to go, we don't have to squeeze, therefore it's irreversible and spontaneous. Guys, why does it happen? What is the driving force that makes this happen, Doug? Exactly. It's disorder. And guys, this is that weird moment in your life where you've got to understand this. Guys, some things in our universe happen simply because it makes the universe messier. Seriously. Guys, this is a driving force in our universe that is just as real as releasing heat. So guys, you got to get comfortable with this, that a driving force in our universe is messiness. That processes in our universe tend towards conditions of greater messiness. Now guys, if you'd like to dig into this deeper, please write this down. Page 794. If you want to learn more about this, you can get into the calculus of microstates. We are not going to do that. But guys, all of this comes down to probability and chance. It's interesting how a lot of things in our universe, including the position of electrons, comes down to probability and chance, but that's a different conversation. But guys, this happens because of messiness. This happens because of disorder. The only reason this happens is because the picture down at the bottom is more disordered than the picture up at the top. So as things spread out, they become more disordered. And guys, Doug used the name for that. We don't call it randomness. We don't call it messiness. We don't call it disorder. We call it entropy. So guys, here's then the deal. You don't need to write this down. But this is actually an isothermal process, which means that the temperature doesn't change. So guys, if the temperature doesn't change, this is not spontaneous. It doesn't go both directions. But guys, the trick then is this. This is a process which increases disorder, and this is what makes it spontaneous. So guys, let's come back to it. Why does the quick cold pack happen spontaneously? Because of disorder. Guys, it turns out that the process of dissolving ammonium nitrate in water increases disorder. And if we want to write it down again, we've got NH4, NO3, and that breaks down into NH4s, and it breaks down into NO3s, and you can almost picture those surrounded by the water. And guys, can you see that that's more disordered? When the salt is all tied together, that's got a lower amount of disorder than it does when these break into individual ions. And as it dissolves, disorder goes up and it makes it spontaneous. Now guys, here's the question. How much energy is lost in the form of disorder? More than is absorbed in the form of heat. Think about that. How much energy is lost in the form of disorder? And the answer is more than is gained in the form of heat. Because if that wasn't true, the process wouldn't happen. We're going to talk more about that later. But guys, what you need to understand right now is the reason this works is because when the ammonium nitrate dissolves, the disorder goes up. Go ahead. We're nowhere near Appendix C. Guys, we're not doing any math today. We're just talking about messed up. We're talking about disorder. You okay? Go ahead. Yes. So the energy, so let's say our system is the ammonium nitrate. The energy of this system is going down because it's going from a position of lower disorder to higher disorder, which is a net release of energy. We don't have a name for it. It's not like endo or exo disorderic, or we don't have a word like exoentropic or something. It's releasing energy in the form of disorder. Go ahead.
So you were showing us like a crystal example.
Yeah.
Like,
Yeah.
you were saying it has a low disorder.
Yeah.
So I was wondering if the disorder would change like when phase change.
Good. How do I do this? Sorry guys, here we go. Let's do that together. Guys, check this out. So what I want to do is I want to come to exactly what you were talking about. And guys, this is not trivial. This was on the AP test 2 years ago. And frankly, it surprised me. In my mind, I thought that this was so, what's the word? Not minute. Such a small topic that I couldn't imagine that it made the cut for the AP test. And it did. And it was really cool that I taught it because my students nailed this question. But guys, here's what we're going to do. So we've got this idea that disorder is called entropy. But let's just keep thinking about disorder. We've got entropy up here, but let's just think about disorder. So guys, what I want to do is I want to play for you the video of salt dissolving in water. And as you watch this, I want you to keep an eye on disorder. And then we're going to talk about, is it going up or down?
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that interact with the ions on the substance, such as sodium chloride, is placed in water.
Okay, so let's go back here. Talk to me about the disorder of that crystal, high or low? Low. Guys, this is forgive me, I should never say this, but this is a highly ordered system. It's a crystal. The disorder is low.
Sodium chloride is placed in water. Water molecules interact with the ions on the surface.
So guys, as this crystal then, I think blue is an okay color to draw with. So as this crystal then is dissolving in water, what is happening to the entropy? What is happening to the disorder of the salt? Is disorder going up or down? Disorder is increasing, and you can actually see that as you watch these ions being carried off into solution.
If the salt is soluble, the attractive interactions with water molecules overcome the ionic
Do you see it? And off they go.
attractions
and
within the
disorder
lattice.
is going up. So guys, when salt dissolves in water, the disorder goes up. Yeah? I would say not completely. Let me keep playing.
The solvated ions move off the surface and become separated.
Do you see it? Because I would propose to you that as you watch this video, disorder is also going down.
Attractions within the lattice.
Where do you see it, Nathan? The water.
The solvated ions move off the surface and become separated in solution.
Guys, what is liquid water like? What's our analogy? A mosh pit, right? It's like crazy chaotic, very high disorder, very high entropy. But guys,
Notice
watch
that
this.
water molecules
Do you see it now? Guys, there is both an organizing and a disorganizing process. And you're going to find out after the weekend when we talk about entropy, we have to include all of the parts of this system, and we don't get to focus on one or the other. So we can then say this: what is happening? Can I just use the word entropy instead of disorder? What's happening to the entropy of the salt? It's going up. What is happening to the entropy of the water? Isn't it pretty how organized it gets? But now, guys, the question is this: which one must be greater? The disorganizing of the salt or the organizing of the water? The disorganizing of the salt, and we're going to talk more about that later. And guys, that is actually the complete answer to what's going on inside of here. The ammonium nitrate is becoming disorganized, the water is becoming organized, but the disorganization of the ammonium nitrate is not just greater than the organizing of the water, it's also greater than the amount of energy that's being gained in the form of heat. And it's a lot. Guys, what you're going to find is this. What are your units for enthalpy? Kilojoules? Guess what our units for entropy are? Joules. They're small. And guys, we're going to quantify this after the weekend. But guys, for now, we just need to be comfortable with the idea that entropy is a driving force in our universe, that things tend towards conditions of greater disorder. And we're going to have to broaden our perspective in order to wrap our heads around this. You guys okay? So guys, let's call it there. Questions or things you want to wrap up on? Please. Here's the thing, Luke, that's a brilliant question. So guys, Luke's question is, can we use this energy? And the answer is typically no. And this is, so Gibbs, right? Gibbs free energy. I don't know if you guys read this or not. Gibbs was actually an engineer. And when I say engineer, I mean like trains. Back in the 1800s, he was trying to figure out how to maximize the amount of energy that a steam locomotive could give off. Because the more, then you could maximize coal consumption to drive your train. And what he was finding was he was losing all sorts of energy. He knew how much energy the coal should provide. He knew how much energy the locomotive was putting into the cars. And there was all this energy that he was losing. Turns out he was losing it in the form of entropy. And so what he did, that's where all of his math came from, was he figured if I can quantify this energy loss, I can reduce this energy loss. And that's where this whole conversation about entropy first started. Because typically, entropy is useless loss of energy. So guys, you know well enough to know you got homework coming. Just a second, leave it. So guys, this then let me do this. Let me stop recording. Well, here. This then is your homework. Let me stop recording.